Hello and welcome, Geography 231 students. This is your week 2 lecture. So, as I mentioned last week in our live Zoom, some weeks I'm going to post an actual video lecture. Other weeks I'm going to post just a tutorial. This week I'm going to do both, a lecture and a tutorial. Some weeks I may just do a lecture and no tutorial at all. So it just depends on the situation. Obviously, we're early in the semester, so I'm trying to maintain as much, provide as much contact as I can at this point. And this is obviously the first time that we've run this class. I've run this class online before, so we're going to try to kind of replace the weekly lecture via video as often as I possibly can. But there may be some weeks when doing a video presentation is not necessary, but this week it is. So I've already recorded a tutorial for exercise 3A from your textbook, Understanding GIS. So that's available along with this video. And so I'm just going to walk you through as if I were standing in front of the class and you were sitting at your seats in front of your computers right now in the classroom in Humanities 316 where we normally meet. So this week, without further ado, this week we are looking at evaluating spatial data. All right, so as I mentioned last week, the first 2 weeks of this class really are primarily to expose you to ArcGIS Pro. So even though this is spatial analysis, this class spatial analysis, we aren't doing too much of it for the last week and this week. Next week will be our last week using the Understanding ArcGIS Pro or Understanding GIS textbook for now. So we're going to be covering exercises 1 through 4 in Understanding GIS, and that will bring us through week 3. In week 4, we're actually going to do some spatial analysis, and I will be introducing some concepts based around the census. So as you know, this is 2020, and in addition to the myriad events, crazy events, planned events, some not planned this year, obviously, with the pandemic. There's also a decennial census. So the decennial means every 10 years. There is the 10-year census occurring this year, where every man, woman, and child in the United States is counted. We get a 100% count of everybody living in the country. That is going on right now as we speak. And so I want to be able to sort of explore that and introduce that to some of you, or dig a little bit deeper for those of you that have had some exposure to census data before. So we're going to basically acquire census data, census geographies. We're going to join them together, and then we're going to do some actual spatial analysis. Okay, so that's the plan for week 4 and 5. So this is our penultimate week using the Understanding GIS textbook. We got one more week next week when we look at building geodatabases, spatial data collection, a little bit more. And so yes, that's just kind of brings us up to where we're at now. So this is week 2, evaluating spatial data. Sorry. Here we go. Okay. So the tutorial, which is available now, looks at exercise 3A. I walked you through the majority of 3A. I didn't do the entire thing because the portion I didn't cover is more or less repetitive of what I did cover. So I think I hopefully will have helped to get to a point where you can pick up and carry on your own. The lab exercises this week that are due obviously are the deliverables that are in our module. Specifically, you will need to upload the data description table. It's I think it is called data requirements is the name of the table. So once you have gone all the way through exercise 2, A, B, and C, and then exercise 3A. Basically, so exercise 2 and 3, all throughout those exercises, you're going to be inputting data into the data requirements table. Okay, so once you've completed that, I want you to upload that Word document to Canvas. That will be one deliverable. The other deliverable is just answering a question, specifically, what is the straight line linear foot distance from the northwest end of the LA River to the southeast end of the LA River, where it intersects with the city boundary. and I want to know in linear feet to the nearest 1,000. So it's in the module, but basically that means that there are going to be two deliverables. One is the Word document. The other one is just text that you will enter into Canvas. Okay. All right. So upon completion of this lecture and lab, you should understand the differences between primary, secondary, and tertiary data. You should understand data validity and reliability, and you should understand levels of measurement. So as the name of this week, or I should say the topic of this week implies, we're going to be evaluating spatial data, specifically ideas of quantitative and qualitative data, various differences between data that you acquire yourself, data that you acquire from others, and then also the quality of the data, validity and reliability, and then levels of measurement. There are ways to measure data outside of the typical quantitative measurements that we often think about, length and width. There are other ways as well we'll talk about. Okay, so evaluating spatial data, primary, secondary, and tertiary data sources. So moving beyond the five senses, we learn about our immediate environment through our senses. Obviously, we have our sense of sight, smell, touch, hearing, and taste. All right, those are the ways that we sense the world around us, the way that we take in information and understand the world around us. But how do we learn about places that are outside of our personal experience? More importantly, in the spatial context, how do we learn about places that are remote from us or distant from us? So if you're sitting at your computer now in Southern California, how do you know anything about some place on the other side of the world? Obviously, we have Google Maps now, which is a really technology that we take for granted. Google Maps started about 15 years ago, and before that, aerial imagery was not that easy for the average person to acquire. But you can do that now. There are obviously other ways to learn about the world around us. But whenever we are trying to sense something or learn something about the world distant from ourselves, it's important to learn about it from multiple perspectives and multiple angles. Okay, so if you only see one portion of a thing that you're studying, you may not get the whole picture. All right, so consider the parable of the blind man and the elephant, and there's a little link there in your lecture notes that I want you to check out. It actually has the text. It's from an old Buddhist text. So basically the parable goes like this. So an elephant is presented to several blind people with, we'll say, sight impaired people. Okay, so only a small portion of the elephant is presented to each individual person. So you imagine a group of, we'll see, 10 people. None of them can see. And so each person is presented just a small portion of the elephant, maybe the head, maybe the ear, maybe the tusk, the trunk, the tail of the elephant. All right, so the people that were the people were presented the portion of the elephant, and then they were asked to describe the elephant, not just the portion they were shown, but an entire elephant. So imagine not having the ability to see and only being presented a small portion of the elephant. You might feel it, you might smell it, you might hear its trunk, right? But basically, if you're only given a small portion, how can you actually describe an entire elephant? So as the story goes, the people were asked to describe an elephant after being shown just a small, or not shown, presented a small portion. The one who was shown just the head said, the elephant is like a jar. All right, so he only felt the head. So he thought an entire elephant was like a jar, like a big head. The person who was shown just the trunk said, the elephant is like a plow pole. All right, so the pole of a plow, because he only touched the long trunk. The one who was shown just the tail said, the elephant is like a broom, right? You can kind of imagine an elephant's tail like a broom, right? So he imagined the entire elephant to be like a broom, and so on and so forth, depending on the portion of the elephant they saw. So this led to much disagreement over what an elephant actually is. Okay. So similarly in research, we're often limited in both the amount and the detail of available data. It's not always easy to get the whole picture. Okay, and so you as a researcher, as a GIS researcher, it's up to you to actually dig as deep as you can and try to approach it from multiple angles. Hopefully, you can find multiple data vintages, maybe data from the current year, data from last year. Maybe if you're looking at say like the physical landscape, you might be able to download like a digital elevation model and an aerial photo. So you have both the terrain and a photo. So it's up to you, the researcher, to try to paint as detailed a picture as possible through the data that you acquire. Okay. So to solve this problem, we gather data from multiple sources using multiple perspectives and ideally multiple methods. That's the hope. Data come in many different forms, but all can be classed into one of three groups: primary data, secondary data, and tertiary data. And as the names imply, you probably can see primary would be like first person data, data that you collect. Secondary data would be you're like second person, so the first a group of people or a researcher collects the data, then you then use it. And then tertiary would be tertiary three. So you're 3 degrees separated from the original data acquisition. So primary data, it's data that's collected directly by the researcher. Maybe you, maybe it's me, right? But it's whoever is doing the research is also collecting the data, his or herself. So this may include direct observation, remotely sensed imagery, maybe with a drone or a satellite if you have access to that. Drone data, obviously a little more easier to access. GPS coordinates collected with a handheld unit. Surveys, maybe actually literally going out to a park and asking people to answer X, Y, and Z questions, and interviews as well. Okay, so what are the advantages of primary data? You obviously, it's your data, so you have a clear understanding of the origins of the data, and the study purpose. So you're not just finding data and shoehorning it into another study. You are designing the research yourself, you're designing the methodology, and you're collecting the data. So it's very much, I will call that a highly reliable study because you have designed it and you've collected the data. You can actually accomplish what you're trying to accomplish because you have planned out the data acquisition methods, and you have complete control of the data as well. You don't have to worry about any sort of like copyright infringement or anything of that, use restrictions. The disadvantages, on the other hand, are that primary data are both time consuming and costly to acquire. You need to have the time to do it. You need to have the money to do it. So if you're maybe a PhD postdoc, you might get a stipend or something to go do research for a year. But if you're an undergrad, you don't always have that advantage, right? So primary data, well, it's great from the perspective of being able to customize your acquisition methods. It takes a lot of time and it can take money. Okay. Secondary data are data that were originally captured by other researchers for another purpose. So I use the example here of census data. Census data is designed obviously to count the number of people in the country, but then there are other subdivisions of that. Lots of questions are asked on the census. It's not just how many people live in your household. It's what's your household income? What are the ages of those who live there? What's the sex ratio of men versus women? What's your employment status? There's all this various data out there that the census collects. Then you as a researcher, you may be trying to answer something else. And so you pull that secondary data, the census data, and then you use it to answer some other question. So maybe you will like triangulate your the answer you're trying to arrive at by taking multiple variables from the census and then kind of creating a story. So maybe you want to find out what's the kind of demographic profile of a neighborhood. Maybe you're trying to figure out is this a prime location for like a coffee shop, and so you might think, okay, so who are the people who like coffee? We'll say it's college students. So you look at the age profile of an area and you want to target an area of those age 18 to 35. Maybe you find out that people who earn an average of $50,000 a year are more likely to spend $5 a day on a cup of coffee. So you look at that demographic profile. What's the average income? So you can essentially take census data, which is obviously when the data is collected originally, it's primary, but then when you use it, it's secondary, and you can then paint a picture and hopefully answer a question that you're looking to answer. So at any rate, secondary data may include census data, aerial imagery collected by someone else like Google Maps, GPS coordinates collected by someone else, digitized hard copy maps, like someone who took an old map and scanned it and digitized it, or peer-reviewed articles. So some other researcher went out into the field, did an entire study, and then you use his or her research to answer some other question. The advantages are that it's efficient, it's cost-effective, and it's timely. The data is already there. It's already been collected. All you need to do is then use it to plug it into your research to answer the question that you're looking for. Disadvantages, these are obviously, it's kind of flipped from primary. You have no control over the original study. The original study's done. There was an original purpose or goal in mind. You're now using it for your own purposes, and hopefully you'll still end up with a valid research study. But just know that something is originally designed for one project. It can often be used in other projects, but it wasn't designed for anything other than that original project. Likewise, if there were any errors in the original data, you will then be inheriting those errors yourself. So you always have to be aware of that. So that's secondary data. Tertiary data are data based on collections of primary and secondary sources. So ultimately, this really just kind of comes down to what you can kind of consider anthologies of data. So a textbook, right? So this here, you can see Understanding GIS is a collection of authors whose primary research was then collected by some other researcher, and then they present it to you. So you're essentially 3 degrees separated from the original research. So textbooks, which can also sometimes be a secondary source depending on the text itself. Scholarly journals. So journals are collections of scholarly articles. Dictionaries, encyclopedias, manuals, guidebooks, directories, almanacs, and indexes and bibliographies. So each of these are tertiary data. The advantages and disadvantages vary, and they may be exaggerated with a degree of separation from the primary source. So just know that any of those advantages and disadvantages we talked about with primary and secondary, those can just kind of be accentuated with tertiary. So you may save a lot of time because you dig into a scholarly journal and you find a bunch of relevant articles. Great. But by the same token, you are also assuming the risk if there are any errors, or if the original studies were just less and less relevant to what your stated goals are. So that's tertiary data. Moving on to data validity and reliability. And these essentially are ways of evaluating the quality of data. So assessing data quality. Data are not all created equal. Data vary in quality. All right, so depending on the methods of acquisition, the methodologies employed, that may determine whether this is high quality data or low quality data. Okay, high quality data are the very foundation of high quality research. So without high quality data, it's literally impossible to have a high quality analysis. Why? Because of the principle of garbage in, garbage out. You may have heard this before, GIGO. So if you put bad data into a project or research analysis, you will end up with bad data output because you can't create something good from something bad. Essentially, the well has been poisoned, so to speak. Okay, so be aware of that. You will never end up with the final product being worth more than some of its parts if the parts are of a low quality. Okay. So data quality can be assessed by evaluating 2 components, validity and reliability. Validity is the extent to which the results of research measure what they're supposed to measure. All right. So a question you can ask is, does your research project really measure what you were setting out to measure? You essentially are asking, is the findings of this research at all in line with what I had originally set out to find? Okay, so maybe you went to find out, and we'll go back to the whole starting a coffee shop example. Maybe you went out to research the demographics of a neighborhood to see if it's appropriate for a coffee shop. What you found is that, hey, it's not appropriate for a coffee shop, but it's really good for a Walmart. Okay, so that's great. You've discovered through looking at a demographic profile with census data that this neighborhood is great for Walmart. Fantastic, but that doesn't help you or answer the original research question, which is this neighborhood appropriate for a coffee shop? Okay, so that would mean that your research data is now invalid. Okay, so validity has 2 main dimensions, internal and external validity. Internal validity is the degree of certainty that observed results measure what they're supposed to. All right, so essentially, did the findings measure the appropriateness of this neighborhood for a coffee shop? No, they found that this neighborhood is appropriate for Walmart instead. Okay, and so that's internal validity, the degree of certainty that the observed results measure what they're supposed to, rather than some intervening, extraneous, or confounding variables. Confounding variables are essentially variables that throw a wrench into the research. These are variables that may, you could say, not disprove, but confound your hypothesis. So you might find, if you're looking at, we'll say, socioeconomic data, you might find that this neighborhood has a very high median income, or say average income. We'll strip the word median for a second, strike that. We'll say it has a very high mean or average income, but it turns out that with an average, it's an average. So you take everybody's income together, you add them up, you divide by the total number of people in the neighborhood. Well, what if it turns out that this neighborhood has 100 households? 10 of those households are really rich. 10 households are people making $1 million a year or more. And then the other 90 are people making $10,000 a year. Okay. So the confounding variable is that you have your data skewed by those outliers. Okay. So that could mean that you have invalid data because outliers have now thrown off the average. All right. So that's internal validity. External validity is a degree to which research findings can be applied to the real world beyond the controlled setting of research. So anytime you design a research project, you are essentially designing it hopefully with a real world in mind, but certainly under best case scenario. Okay, so you're saying if all of these various phenomena occur, then this is the scenario that we're hoping to recreate. Well, if your research findings cannot be applied in the real world, then is the data really valid at all? The answer is no. Okay, so that's validity. So here is a scenario for you to consider, still keeping in mind the concept of validity. Suppose you're studying the prevalence of California condors along the California coast. You could collect primary data through first-hand observations at random locations along the coast between San Francisco and Santa Barbara. The California condor's habitat tends to range between San Francisco and Santa Barbara along the coast and also in the mountains there along the coast. Okay. Again, the scenario is you're trying to study the prevalence of California condors along the entire California coast within this area. Okay, so you could collect primary data at random locations, or you could collect primary data through first-hand observations in the Los Padres National Forest and San Rafael Wilderness. But consider, some locations in California have been set aside as prime condor nesting grounds, including the Los Padres National Forest and San Rafael Wilderness. So you have to ask yourself, are first-hand observations of California condors within prime nesting grounds valid data if the research is explicitly designed to evaluate prevalence of condors along the entire California coast? Think about that, right? So if the goal is to get an accurate representation of the prevalence of condors along the coast between San Francisco and Santa Barbara, but you spend your time in an area known for prime nesting, odds are the nesting grounds are going to be a confounding variable. Those nesting grounds are going to inflate the numbers of condors because you are essentially hanging out in their best case neighborhood, like this is where they want to be. So no, valid data would include random samples along the coast without favoring areas with an inordinately high incidence of condors. Okay, so just keep that in mind. You can kind of apply that to any kind of research. If you're trying to get a random sample, you need to make sure that you are actually randomly sampling as opposed to favoring or cherry picking one area that you know is going to have a prevalence of whatever you're looking for, in this case condors. So as Joe Condor there says, don't inflate my numbers with shoddy research, dude. Okay. All right. So that's validity. Reliability is the extent to which the results of research can be reproduced when the research is repeated under the same conditions. Essentially, reliability is the other word could be a repeatability or replicatable. Is it replicatable? Okay. So do your research methods provide accurate and consistent measurements over time, and are the methods repeatable? So if you, we'll say we'll go back to the California condor example. If you went into the Los Padres National Forest and I forgot the name of it already, the San Rafael Wilderness. If you go into those areas and you find this high prevalence of condors, but then you present your data as if you took random samples, and then another researcher who's also looking at the prevalence of California condors does do a random sample, and they find the numbers to be significantly lower than yours, then your data was not reliable because your methods were not equally reproduced because you didn't present the actual methods implied. Okay. So all research procedures related to data collection, measurement, and data entry should always be documented, well-defined, and consistent. So whenever you do research, you always have to document every single step along the way so that your data may be reproduced by another researcher. Okay. And you'll find hopefully, at least even in this class, when you work on your research paper, if you start to read journal articles, you'll find that a lot of papers have literature reviews. They review other literature or research projects that are related to the topic of that paper. Okay, we call it a lit review. The reason why researchers do that is they will often reproduce other people's methods, right? And that's okay. It's completely okay to do that in the academic world as long as you cite your sources, you cite the inspiration for the research, and you don't literally duplicate the entire project, but you take the methods and you apply them elsewhere. Okay, so in geography, it's easy to do that. You can find a really great project that was, or say a research project that was conducted in London, and then you can apply it in Los Angeles, right? Because it's all about space. So you might want to be measuring the same phenomenon, but in a different location. So you can do that. So a reliable measurement is not always valid, something to be aware of. Reliable measurements are not always valid. Results might be reproducible, but they're not necessarily correct. Okay, so you might be able to reproduce someone's study, but if the original study was incorrect, yours may be incorrect too. So it's reliable, but it's not valid. Okay, so check how results correspond to established theories and other measurements of the same concept. So that's this concept that you want to always compare your research to others and make sure that the expected outcomes are tracking along with the actual outcomes. And here I just have a little cheat sheet for you to kind of help remember, let this sink in. So validity versus reliability. What does it tell you? Validity is the extent to which the results really measure what they're supposed to. How is it assessed? By checking how well the results correspond to established theories and other measurements of the same concept. And how does validity relate to reliability? A valid measurement is generally reliable. If a test produces accurate results, they should be reproducible. For reliability, what does reliability tell you? It's the extent to which the results can be reproduced when the research is repeated under the same conditions. How is reliability assessed? By checking the consistency of results across time, across different observers, and across parts of the test itself. Finally, how does reliability relate to validity? A reliable measurement is not always valid. The results might be reproducible, but they're not necessarily correct. So keep that in mind. Oops. All right, and finally, we're going to wrap up with levels of measurement, looking at different ways of measuring data that may not always be quantitative. Okay, so when we talk about quantitative, it's quantity, numbers. So oftentimes, we most often think about measurements as width, length, height, time, things like that. But how do you measure a color, for example? You can't measure a color, but you can class it in a way that's logical. Okay, so here we go. So unlike positions, sizes, and distances, certain non-spatial characteristics of features located on the Earth's surface are not always easily measurable. So for example, how do you measure a name or count a color, right? So in response to this situation, this scenario, where you might need to be able to measure non-quantitative features, a psychologist named S.S. Stevens outlined a system of 4 levels of measurement in 1946. This was meant to enable social scientists to systematically measure and analyze phenomena that cannot simply be counted. And then these levels of measurement, are nominal, ordinal, interval, and ratio. The 4 levels are important to GIS users because they provide guidance about the proper use of different statistical, analytical, and cartographic operations. In the following slides, Stevens' original 4 levels of measurement are defined and discussed in the context of GIS. So nominal, as I always tell my students, the way to remember nominal, think name. Okay, so the name of an object is its nominal characteristic. Okay, nominal data are mutually exclusive but not ordered. That could be streets. For example, I live on a street, we'll say Main Street. Next door could be Grand Street. Next over could be Simple Street. Okay, so those are 3 different streets. They all have a unique characteristic, so they're mutually exclusive, right? Main, Grand, and Simple, but they're not ordered. There's nothing about the length of the street or the width of the street. It's just that they all have a mutually exclusive characteristic, so that's its nominal value, okay? Oftentimes in GIS, qualitative data are nominal data, okay? So maybe observed and described, but not directly measured. So in the GIS context, qualitative data would be like names, ordered, not ordered, names of places, nationality, ethnicity, languages, biological species, ground cover, geological features. Okay, so these are all unique and mutually exclusive features. So when it comes to nationality, we've got Canadian, American, Mexican, right? Languages, French, English, Spanish. These are all nominal characteristics, even though they cannot be ordered, right? You can't order a nationality from like smallest to largest or first to last or something like that. So they're different, they're unique, but there's not any sort of order there. So the easiest way to remember nominal is a root word nominalis, nom like name. Okay, so maybe differentiated into different groups and categories. We then call it categorical data, but it can't be logically ranked. So if you see here on the slide, the different categories here are types of vegetation: woods, scrub, orchard, vineyard, mangrove. Now, these are all types of vegetation. Maybe you got different types of woods: pine, coniferous, deciduous types of trees, but they can all be classed into wood. Okay, so that's nominal. Ordinal data is like nominal, but there's some sort of order involved. So again, you can't count it. They're not quantitative, but you can rank these data. Okay, so ordinal data assigns observations to discrete categories based off of rank order. Okay, so think about low, medium, high, first, second, third, small, medium, large. National. Think about hierarchies of borders rather. National border within nations are states or territories. Within states and territories, you have counties. Within counties, you have cities. Within cities, you have neighborhoods. Okay, so from large to small in that case. So how do you remember ordinal? What does that mean? Think rank order, ordinal order. All right. So these data cannot be measured outside of extrinsic preferences. So extrinsic, low, medium, high, first, second, third, poor, okay, and best, right? Or good, better, best, something like that. Okay, so these are extrinsic values that are placed on them. They have no intrinsic value. Okay, so there's no intrinsic value to national borders or state borders or county borders. These are all things that have been superimposed on the landscape from without. All right. So the act of prioritizing nominal data into categories and giving them order makes them ordinal data. If nominal categories follow some sort of logistical hierarchy, then they are then ordinal data. So just think ordinal data, order, low, medium, high. Next up, we move into a more quantitative perspective. Okay, interval data are data that can be measured. So these are data that do have maybe a length or a width, height, something like that. These are data that have a quantitative aspect. They can be measured, and the difference between values is meaningful, meaning that there's a interval difference from one value to the next. The examples I have here on the slide are the difference between 80 degrees Fahrenheit and 90 degrees Fahrenheit is 10 degrees. And that's the same as the difference between 90 and 100 degrees Fahrenheit, right? So the difference between 40 and 50 is 10 degrees. The difference between 80 and 90 is 10 degrees. So there is a meaningful difference from one value to the next. Measurements exist along a continuous number line, meaning that with the example of temperature, once you get down to zero, you can go below zero, right? Whether it's 0 Fahrenheit or Celsius, there is something below that, right? If it's Fahrenheit, below zero is very, very cold. If it's Celsius, below zero is cold, but it's below freezing, but it's just barely below freezing, right? So what that means is that zero in this case is arbitrary. Zero couldn't be anywhere along a number line. If it's Celsius, it's over here. If it's Fahrenheit, it's over here. So the number zero has real no significant meaning, but there are measurements that fall above and below it. Other examples of interval data might be the year. So we use the birth of Jesus as our, starting year one in the West, right? The Western calendar, the Gregorian calendar. Are we on? I think we're on the Gregorian calendar. Zero. I don't know if there was a year zero. There's one BC and there's one AD, right? Or BCE and one CE, right? So zero is arbitrary. Jesus had been born a different year. The year one would be other. If you use like an Islamic calendar or a Jewish calendar, then year zero is another time altogether, right? So again, the zero there is essentially meaningless. You can be negative numbers, you can be positive numbers, and a good geographic way to understand that is with elevation. So sea level is at 0 feet, right? 0 feet above sea level, you're at sea level. You can go above sea level. You can also go below sea level. So looking at the lecture slide there, you can go down to the Marianas Trench, right? 20,000 feet or whatever, 29,000 feet below sea level. Or you could be on the top of Mount Everest, 29,000 feet above sea level. So that 0 is, it's not arbitrary on Earth, but you can go above and you can go below. Lastly, we have ratio data. With ratio data, it has all the same properties of interval plus a clearly defined 0, meaning that 0 is the bottom. There's nothing below 0. There are no negative values in ratio data. That's the key thing to know. So measurements exist along a number line with an absolute 0. If you go below 0, you're at null. There's nothing there. Okay, so measurements must fall at or above 0. Examples: height and weight. So I'm 6 feet tall. If somebody was 0 feet tall, they wouldn't exist, right? If they're 1 inch tall, they would be an embryo or something, right? So essentially, there's a meaningful, clearly defined 0 in this case. Distance is the same. You can go 10 miles, you can go 1 mile, but you can't go negative 10 miles. Okay. Area, same thing. Acreage, you can't have negative area. And then another kind of interesting kind of just quirk here is that with temperature values, if you use the Kelvin scale, temperature scale, 0 is absolute 0, and there is nothing colder than absolute 0. That's the point at which molecules stop vibrating, essentially. I think I got the phrasing there right. But basically, it's the coldest temperature there is. There's nothing colder. So absolute 0, there is no negative 5 Kelvin. Okay, 0 Kelvin is, that's it. That's death. That's entropy right there. All right, so be aware of that. Okay. So moving forward from that, I've got a little bit of a cheat sheet here listing the levels of measurement put into categories. All of those can be put into categories: nominal, ordinal, interval, and ratio. Data arranged in order. You cannot do that with nominal, because think about that. That's like grasslands, scrublands, desert, or tundra, right? So they're nominal. There's a unique difference, but they can't be put into order. Add and subtract values. You can't do that with ordinal data. Think about small, medium, large, first, second, third. There's no addition, subtraction there, whatever. Those are extrinsic values applied to groupings. Lastly, can you determine if one data value is a multiplier of another? You cannot do that with interval data, but you can do it with ratio data. Okay, so that's your cheat sheet. All right, so that actually is going to conclude this lecture verbally, but continue through the slides. I basically have presented examples from a cartographic perspective, and these are going to be useful to you, so I do encourage you to go through them, but I am not going to walk you through because we're coming up on 40 minutes, and I think that is enough time. Go ahead and quiz yourself here if you want. That's a lot of fun, actually, if you can kind of answer these questions. The answers are there, but it's good to see if you can answer on your own. And then here are some examples of cartography taking into account the different levels of measurement. Here, let me just show you this real quick. So trees by species, this would be nominal data. On this map here, we've got a data set of trees that have been sensed in the city of LA. GPS coordinates were basically taken at each tree location, and then characteristics about the trees were marked down. So we got type of tree: pine, eucalyptus. I can't read the other ones here on my screen. Different types of trees. There's the same data set, but looking at it ordinally. All right. So foliage quality: poor, adequate, excellent. Those aren't characteristics that can be added or subtracted. They are extrinsic values: poor quality, adequate quality, or excellent quality, but they can be ordered, all right, from worst to best. Next up, tree height in feet. This is ratio data, right? So we can have a tree that's brand new, it's like an inch tall, or we can have a tree that's 90 feet tall, but you can't have a tree that's negative 10 feet tall. And there's a couple other examples. So you can go through that on your own. But at any rate, that will conclude this week's lecture. If you have questions, go ahead and drop me an email or post on the discussion board. Yeah, until next time, have a good night. Bye-bye.